This is problem number 3 of International Math Olympiad 2014. Convex quadrilateral ABCD has two right angles, ABC and CDA. Point H is the foot of the perpendicular from A to BD. Points S and T lie on sides AB and AD respectively, such that H lies inside triangle SCT. And the difference between measurements of angles CHS and CSB equals 90 degrees. Also, the difference between measurements of angles THC and DTC equals 90 degrees. Prove that line BD is tangent to the circumcircle of triangle TSH. This problem is a good test of our knowledge of plane, P-L-A-N-E, geometry, that was well known to ancient Greek mathematicians such as Euclid, Archimedes, and less known but not less significant Apollonius, who lived circa year 200 BC. I will explain the official solution given on the IMO website. Let's start with a simple observation. Since the quadrilateral ABCD has two opposite internal angles that are both right angles, this quadrilateral is cyclic or cyclic, whichever you prefer. In any case, it means that there exists one circle to which all 4 points A, B, C, and D belong. And that implies that a pair of blue angles have equal measurement because they both are inscribed angles in that circle that are subtended by the same chord AD. Let's remember it as fact number 1. Let us draw points S and T on sides AB and AD respectively, as the problem describes, and let's draw perpendicular bisector lines to each of the segments SH and TH until they intersect with their corresponding sides on one end and with the segment AH on the other end. The point of intersection of these two perpendicular bisectors is the circumcenter of the triangle TSH. Obviously, if this circumcenter lies on segment AH, then the radius drawn from that center to point H will be perpendicular to the side BD, which means that BD is tangent to the circumcircle. We can easily see by looking at the drawing that two triangles SHB' and THD' are both isosceles triangles in which their corresponding perpendicular bisectors are also angle bisectors. So we can apply the well-known theorem about the angle bisector, which states that angle bisector divides the opposite side of a triangle in two segments whose lengths are proportional to the corresponding side lengths, from which we can conclude that the point of intersection of these two angle bisectors with the side AH of the triangles AB'H and AD'H is the same point if and only if the ratios of side lengths HB' to AB' and HD' to AD' are equal. So, the proportion written on the diagram is equivalent to the statement of this problem that the circumcenter of triangle TSH lies on the segment AH. Now it's the most interesting part. The proportion that we saw on the previous diagram is about the distances of 2 points A and H from B' and D'. Actually, there is an infinity of such points, like A and H, that have the same ratio of their distances from points B' and D'. And such points form a circle, which is called the circle of Apollonius, of points B' and D'. The center of this circle is located on the line that goes through these 2 points called focal points, and the radius XA is tangent to the circle that goes through these 2 points B prime and D prime, and obviously point A. This is the illustration of a set of Apollonial circles from the Wikipedia article about them. The infinite set of orange circles that go through 2 fixed points A and B. And if we draw a tangent line to any of these circles at any point on an orange circle until intersection with the horizontal line that goes through the 2 foci points, then the circle with the center at that blue point and the radius that is drawn to the point of tangency is Apollonial circle, whose all points have the same ratio of distances from 2 focal points A and B. Let's go back to our diagram. Since the Apollonial circle must go through points A and H, and its center must lie on the continuation of line B prime D prime, then the center of the circle is point X, which is the point of intersection of the continuation of line B prime D prime and the perpendicular bisector of segment AH. Hence, if we prove that XA is the tangent line to the circle that goes through 2 points B prime and D prime and point A, that will prove the statement of this problem, since the Apollonial circle with center X will have 2 radii, XA and XH, which means that 2 points A and H lie on that circle and have the same ratio of distances from focal points B prime and D prime. The fact that line XA is tangent to the circumcircle of triangle AB prime D prime is equivalent to the fact that the angle XAB prime has the same measurement as XD prime D. This follows from the well-known tangent chord theorem. Now let's bite the bullet and prove the equality of these 2 angles. Let's prolong the straight line on which we already have points A, B, B prime, and S, and put one more point on it, point Q, of intersection of this line with the circumcircle of triangle CHS. So we have the circle with 4 points on it, C, H, S, and Q. From that, we can conclude that the angle CQS equals 180 degrees minus angle CHS. Now we can use the condition of this problem, which states that angle CHS minus 90 degrees equals CSB. From that, it immediately follows that angle QCS is 90 degrees, from which we can conclude that QS is the diameter of the circumcircle of triangle CHS. Since point B prime lies on the diameter of the circumcircle of triangle CHS, and at the same time it lies on the perpendicular bisector of segment HS, B prime is the circumcenter of triangle CHS. And in the analogous way, we can prove that point D prime is the circumcenter of triangle CHT. If we draw a straight line through points B prime and D prime, then this line between circumcenters of triangle CHS and CHT is the perpendicular bisector of line segment CH, which is the common chord of these 2 circles. And now if we denote by letter Y the midpoint of segment AH, then XY is the perpendicular bisector of side AH. And from that we can conclude that point X is the circumcenter of triangle CHA. From this we can deduce fact number 2. the angle ACH, which is an inscribed angle in that circle, has measurement half of the measurement of angle AXH, which is the central angle of the same circle, subtended by the same arc AH. So angle AXY, half of this angle, has the same measurement as angle ACH. The last fact that we need is fact number 3. Two angles, HCD and XD' have equal measurements. This follows from our result that line B'D' is perpendicular to segment CH, and side AD of quadrilateral ABCD is perpendicular to the side CD. From that, we have two similar triangles whose internal angles are marked with red and blue colors. The remaining angle arithmetic is self-explanatory. We're done.